Hello friends, welcome to my another video lecture on MOSFET characteristics. Already in my previous videos I started discussion on different MOSFET characteristics, that is ID versus applied gate to source potential, that is ID versus VGS, and ID versus VDS, that is ID or drain current versus applied drain to source potential. Okay, gate to source potential, we got kind of parabolic type of graph increasing. ID increases parabolically with respect to increase in the VGS after the threshold voltage VT. But what we got when I was discussing about the ID variation or drain current variation with respect to drain to source potential, then initially we thought if VG is kept constant and we keep varying VD, so what will happen as we keep on increasing VD, this free electron channel which is formed in between source and drain will basically acting like a resistor, and as a result if we plot the current in the y-axis, that is suppose this is drain current or ID and this is applied VDS or drain to source potential, then we got some kind of graph like this. This is because almost linear graph, and this follows V is equal to IR relation. From the relation of V is equal to IR, okay, we got this kind of graph intuitively. Now after that we have also observed that as we keep on increasing VD, keeping this VG, that is gate voltage, as constant, what will happen after a certain amount of gate voltage? The electrons when as the as electric field increases in the channel, so as a result what will happen, the electrons will try to move from source to drain, that is from negative to positive potential. As a result their potential energy will decrease and kinetic energy will increase. Increase in kinetic energy means increase in vibration in the charged particle, and as a result if the vibration increases, so that the mu or the mobility decreases, and as a result velocity decreases, and for that ID or drift current we can also say goes to some saturation value at a high value of VDS, right? Okay, this we got as velocity saturation. Initial idea, see, let me summarize this. Initial idea was this one. For constant VGS we got almost linear kind of graph. Then we have seen carrier drift, where we got these two relation, VH equal to mu v into E or VE equal to minus of mu n into E. Whatever, we got the velocity proportional to electric field initially, but later we have found out that in semiconductor, as we keep on increasing electric field, after a certain amount of increment, the velocity saturates, because at very high value of electric field, the mobility decreases. Okay, so we have already discussed all these kinds of things. These mu versus E graphs also I have discussed. If you want to know the detailed explanation, just go through the link given in the description. Okay, and as mu mobility versus electric field graph is like this, so that we got velocity versus electric field graph like this, and we know ID equal to any VDA, that is I proportional to V, so that current or drift current or the drain current versus the electric field, or rather we can say VDS, that is drain to source potential graph will be looking like this, because electric field is nothing but this voltage by length of the channel, which is basically, obviously we can say whatever ID, how ID will vary with respect to electric field, same format it will vary with respect to VDS. Okay, so that we got after a certain amount of, suppose let me draw here one vertical line. Suppose after this voltage, what will happen with further increment, the for a constant VGS, ID becomes saturated. Now you may think one question may arise in your mind, that suppose I keep on increasing VDS, so that whether we will get constant ID for whole the region up to infinity? No, it will not happen. Basic electronics concept says after a very high value of VDS, the MOSFET should not work, it should burn, or it should go to breakdown region, right? So basically that's what happens in electronics. If we have suddenly apply very high voltage in LED, think it with respect to real world, when you do experiment in your digital logic design lab, what you do? Suppose by mistake you have applied very high value of voltage across the LED without putting any safety resistor, what will happen? The LED burns out. Similarly, every electronics has a particular it can sustain to a particular amount of voltage after the breakdown should occur. Okay, so that this graph also have some problem, okay, that you should have to identify. How? breakdown of the device can occur. That's what I am going to discuss in my this video. So that our today's topic is modification of MOSFET characteristics because of breakdown. Already we have studied original characteristics, then we have introduced velocity saturation. Now we are further introducing the breakdown concept and we will modify the MOSFET characteristics graph in our this video. Okay, right? Now see, carefully observe this figure. Already I have explained in detail in the physical structure and device operation of MOSFET, where we are applying positive Vg which is greater than threshold voltage, so the free electron channel is formed just below the insulator in the p-type substrate. Body is grounded, source is grounded, or rather you can say body is short circuited with the source and the source is grounded, and then in the Vd or in the drain terminal we are applying positive potential so that electrons will start flowing from the source via the free electron channel to drain. So as a result, in reverse direction the current I will flow, which we call ID or drain current. Now you carefully observe, you are keep on increasing this potential. How the device can burn out or break down, go to breakdown region, just try to think in very logical manner. See, no need to remember anything, just carefully observe this figure and tell me, is there somewhere PN junction is in reverse bias? Because breakdown occurs in reverse bias, right? Zener or avalanche breakdown we have already studied in detail in semiconductor device and circuit course. So our first motto will be, is there somewhere such region is present where the PN junction will be in reversed bias? Okay, yes, that is present. Observe the drain and body or substrate junction. Drain is N plus, that is here high doping concentration of pentavalent is there, and here p-type substrate. This PN junction you observe, p-type substrate or body is connected with the ground, and this n-type drain is connected with the positive potential Vd. That means n-type is at higher potential, p-type is at lower potential. So obviously this is in reverse bias and you are increasing the reverse bias potential. So what will happen? This particular PN junction will go to breakdown after certain time. Okay, and this breakdown will be obviously avalanche breakdown. Okay, what will happen? See, p-type substrate and n-type. Okay, the electrons will penetrate. Okay, from the, as you keep on increasing Vd, actually there is a concept of hot electron effect which you will come to know later. Already I have uploaded that video. If you want to know, you can go through the link given in the description. Actually here avalanche breakdown happens. How? The electrons which are there in the channel, they penetrate this barrier potential and they go to the drain because of their means they are very highly energetic, because very high voltage we are applying in drain. At very high drain potential it happens only. Now when the electrons enter in the n-type drain, then what will happen? Their energy is so high that they will break the bonding in between in the crystal. Okay, as a result electron and hole pair will generate. Now you think, if in the drain electron and hole pair is generated, what will happen? In the drain we are applying positive potential, so obviously hole will get repulsion which are generated just now due to avalanche breakdown. So as a result what will happen? Holes will come to the body, okay, and electrons will go through this path which are generated due to avalanche breakdown. So electrons will come out of the drain. So in the reverse direction what will flow? Current will flow. So basically, as due to avalanche breakdown there is high amount of formation of electron hole pairs in the drain. So as a result, two effects will be there. One is ID or drain current will increase because electrons will come out of the drain terminal. So in the opposite way we can say current will enter, because current flow direction is the reverse direction of electron flow direction. And moreover, one more thing will happen. See, up to now whatever we have considered, we are considering only current with respect to source, but now there is body current also, because the newly generated holes due to avalanche breakdown will come to the body due to repulsive force which is created between positively charged holes and the positive potential applied in the drain, so that they will come to body and they will flow through the body terminal. So that now in this case we will get a big amount of what? Body current also. So hot electron effect is important. What is hot electron effect? If you want to know, you just go through the link given in the description. Okay, so obviously, or if you don't want to explain hot electron effect, then also you can simply understand that as the drain and body are in reverse bias, it is very clear from the circuit itself. So as a result, what will happen? At very high value of reverse bias voltage, the breakdown will occur. As breakdown will occur, what happens? Current increases rapidly, so the ID will increase very much, and due to a breakdown, whatever holes will generate, they will come to body and they will generate body current. Okay, they will go through the body terminal from the substrate, p-type substrate to ground. Okay, that's all. This is the moral of this story. So now let's summarize this. Avalanche breakdown can occur at high VDS, high reverse bias potential, okay, in the reverse bias junction between drain and body. This is very important. These are the keywords. If you want to write some notes, this must be there in the avalanche breakdown, that when the PN junction is in reverse bias, okay, in between drain and body, okay, at very high VDS only avalanche breakdown will occur, and avalanche generated electrons are swept to the drain. Why? You can clearly understand that electrons are negatively charged and we are positive, we are giving positive charge in the drain, so obviously electrons will be attracted, whereas avalanche generated holes are swept into the body because holes are positively charged and we are applying positive charge in the drain, positive potential in the drain, so holes and drain potential will repel each other, so that holes will come to the substrate, resulting current through the body terminal. Okay, so question may be twisted like this: how body current generated? Explain in your own way. You understood this story, you write in your own language, that's all. So now see what was our the heading of our today's discussion: modification of MOSFET characteristics. Now we understood, okay, fine, ID increases rapidly due to breakdown, but how we have to modify the graph? Very easy. See, already we got this kind of graph. This is due to resistive behavior of the channel, and this part is due to velocity saturation for a constant VGS with varying VDS. Now what will happen at very high value of VDS? The avalanche breakdown will occur, and you know, in breakdown the current increases rapidly with a very small change in voltage. Although you increase the voltage very small amount, but current will increase a very large amount. Okay, so that current will increase like this. Okay, that is very high increase in the ID or drain current due to very small increase in the VDS. Okay, so this is the complete graph of the MOSFET characteristics, where we are plotting in y-axis drain current and in the x-axis applied VDS or drain to source potential. Obviously one thing is clear, that just try to understand, MOSFET is controlled by gate voltage, right? Until you apply for this NMOS, until you apply positive potential more than threshold voltage in the gate, there is no question of current if you don't consider this sub threshold conduction or like those. So what will happen? Main gate is the controller, but here after breakdown, see, the gate effectively loses control over drain current. This is very important. Although gate is the controller, but as breakdown occurs, so now gate cannot control, current is uncontrollably increased. Okay, so for constant VGS with keep on increasing VDS, the ID versus VDS graph will look like this. Three regions, carefully understand. If you have any doubt, you can ask in the comment section. Three story, three different, completely different picture and completely different explanation. This part you can classify like this. This is suppose A part, and this part is suppose B part, and this after when current increases rapidly, suppose the C part. A part is due to channel's resistive behavior. B part is after a very high increase of VDS, the velocity saturation or mobility degradation will occur, due to which current saturates. Then after that, if you keep on increasing VDS after a certain voltage, breakdown will occur. Okay, so this is very important. I hope the picture is clear to you. Understand it very clearly, because these are dates. This you must have to understood if you are dealing with MOSFET, whether VLSI or semiconductor device or circuit or whatever linear integrated circuit also, because today we are only using MOSFET. Today ultra modern technology we are using MOSFET also is like kind of age-old technology. At least you should understand this. Today we are dealing with FinFETs. Okay, FinFET is far more advantage, has far more advantage than MOSFET. Okay, to understand FinFET also, at least you should understand the MOSFET clearly. Okay, so this is all for my this video, and this ends the complete explanation of the MOSFET characteristics graphs. In my next video onwards, I will enter into the mathematical derivations of the drain current for VDS and VGS relations. Okay, so this is all for my this video. Thank you for watching.